Dear friends, I myself, Dr. Bharat Parab, discussing the topic Theorem, Conjectures and Axioms. This is covered in Appendix 1. Now we will see the definitions of all three definitions. Okay. The first one, definition of theorem, a mathematical statement whose truth has been established or proved. Okay, the statement is proved is called a theorem. Examples of theorem, read this very carefully. Okay, addition of two even numbers is always even. Okay, second one, the sum of the interior angles of a triangle is 180. And third one, the product of any three consecutive even natural numbers is divisible by 16. We have given the proof of all these three somewhere in this topic. Okay, so we will see this. Okay, conjectures. A conjecture is a statement which is believed to be true. Okay, its truthness depends on the mathematical understanding and experience. Okay, we will come across this. Okay, this may be true or false. But if a conjecture could be proved to be true, then it becomes a theorem. So here we can see the connection between theorem and conjecture. Okay. Now little more about the conjectures. Conjectures are generally outcomes of patterns or intelligent mathematical guesses. Okay. We will see what are these. Okay. Let us see some patterns and try to extract some conjectures out of it. Okay, got it? So, for example, take any three consecutive even natural numbers and add them. Okay, three consecutive even natural numbers. Okay, here 2 plus 4 plus 6 is 12, 4 plus 6 plus 8 is 18, 6 plus 8 plus 10 is 24. We are taking three consecutive even natural numbers. Okay, so like that 24 plus 26 plus 28 is 78. Okay, now this is a pattern. What pattern do you observe? Okay, what can we conjecture about them? Okay, looking at this answer. First one conjecture will be this. Okay, looking at this will be the sum of the three consecutive even natural numbers is even. All these are even. Okay, that is one simple conjecture. And second one, the sum of the three consecutive even and natural numbers is divisible by 6. Okay, if you observe, all these are divisible by 6. So that is how pattern gives rise to conjectures. Okay. Consider the following pattern of numbers called Pascal's triangle. This is very famous Pascal's triangle in maths. Okay, this represents number of line and this represents a sum of the numbers on that particular line. Okay, you'll see this line 1, 1, so sum is 1, 2 raised to 0. Line 2, 1 and 1, addition is 2, 2 raised to 1. Line 3 is 1, 2 below this one and 1, 1, 2, 1. So addition is 4, 2 raised to 2. Line 4 is 1, then 3, 3, 1. Addition is 8, 2 raised to 3. If you see, addition is 2 raised to that number which is 1 less than the particular line. For 4 it is 3, For 5 it is 4, that 5 you get 1, 4, 6, 4, 1, 16 2 raised to 4, like that. Okay, now 6 it is 2 raised to 5. Now see, following this pattern to addition of the seventh line will be 2 raised to 6, 64. No need to write all these numbers and actually add them. Okay, we can just look at the pattern and decide. Okay, so what can you conjecture about the sum of the numbers in line 7 and 8? See, we can see the numbers in 7 is 64, 7 line. Okay, 64 2 raised to 6, or to see the pattern is number of line minus 1. 4 is for fifth. Okay, this 3 is for third, like that. So 2 raised to 6, that is 2 raised to 7 minus 1. And for 8, it will be 128 is 2 raised to 7, or 2 raised to 8 minus 1. So similarly for 20th line, it will be 2 raised to 20 minus 1, or is equal to 2 raised to 19. In general, we can see the sum of numbers in nth line will equal to 2 raised to n minus 1. Okay, this is what we can guess by the having a look at the pattern of this. Okay, now consider another pattern. Okay, we have seen this before. 1 dot t1 is 1. Now 1 dot and again 2 dots is t2 equal to 3. 1 plus 2 is 3, addition. 1 and 2 dots and 3 dots, so t3 is equal to 6. 1 plus 2 plus 3 is 6. 1 dot, 2 dots, 3 dots, 4 dots, t4 is 10. 1 plus 2 plus 3 plus 4 is 10. So we can see here t1 is equal to 1 into 1 plus 1 divided by 2. Okay, so that is 2 upon 2 is 1. We'll just see. Now t2 will be as 1 is 1 into 1 plus 1 divided by 2. So t2 will be 2 into 2 plus 1 divided by 2. That is 2 into 3 upon 2 is 3. Got it? T3 will be 3 into 3 plus 1 divided by 2. That is 3 into 4 upon 2 is 6. T4 is 4 into 4 plus 1 divided by 2. That is 4 into 5 upon 2 is 10. Like that, T6 will be all 1 plus 2 plus 5, 5 plus 6, all this. Okay, equal to 21 is 6 into, I'm talking about 6. 6 into 6 plus 1 divided by 2 is 6 into 7 upon 2 is 21. So now in general, can say Tn is 1 plus 2 plus 3 till n, get n into n plus 1 divided by 2. You have seen this 6 into 6 plus 1 divided by 2. Everywhere this is there, like that. We follow the same pattern. Okay, so Tn is equal to n into n plus 1 divided by 2. As per pattern, we can predict Tn correctly. Okay, hence we could conjecture about Tn that what it is. Okay, so we study some pattern and then conjecture. Okay, this may not be the case if pattern is not correct. Not that all patterns are correct. Okay, whatever we have seen, these are patterns. Okay, so you have to know what do you mean by patterns. Okay, now consider this very nice example. Okay, if a number ends with 2, 3, 7 or 8, that is if units place is 2, 3, 7, 8, then it can never be a squared number. Okay, this is an example of a conjecture based on mathematical guess. Okay, so like that conjecture is given. Now this is again a very intelligent conjecture given by some intelligent mathematician. Okay, another example of conjecture is that Goldbach conjecture, okay, which states that every even integer greater than 4 can be expressed as the sum of two odd primes. Remember, two odd primes. Okay. So, for example, 8, see here, even integer greater than 4. Okay. 8, 1 plus 7, 22 is 3 plus 19, etc. Okay. So, this is an example of a conjecture based on intelligent mathematical guess. Okay. So we see here conjecture. A conjecture is a statement which is believed to be true. Its truthness depends on the mathematical understanding and experience. Okay. So conjectures are generally outcomes of patterns or intelligent mathematical guesses. Okay. Got it? What is conjecture? Okay. So we move ahead. So definition of axiom. Okay. Statement which is assumed to be true or self-evident truth and are proved is called axiom. Okay, we will come to know after reading all this. Okay, some of these statements are taken directly without asking for proofs. However, nowadays axioms and postulates are not distinguished. Some of the Euclid's postulates are as follows. We have seen these postulates in some other topic. Okay, just revising them just to see the definition of axiom. Okay, the postulate 1, a straight line may be drawn from any one point to any other point. Okay, and postulate 3, a circle can be drawn with any center and any radius. Okay, now look at this comment. These statements seems to be perfectly true, and Euclid assumed them to be true because these are self-evident truths. Okay, so these are axioms. Now you came to know what is axiom? As statements which are self-evident truth. Okay, but we cannot accept everything like that, as there are some such things which are confusing or appear to be true but are not always true. For example, the first example, it seems that a number obtained by multiplying two numbers will be greater than both the numbers in picture. What does this mean? Just see, that is, if A into B is C, A into B is C, then C will be greater than A or B. Okay, okay, seems to be true. But look at this, 5 into zero point 0.2 is 1 and 1 is not greater than 5. Okay, so that is what we were talking about, that some statements are confusing or appear to be true but are not always true. Okay, another example on next slide. Okay, second example, now consider these two lines and try to find out which is longer, A or B. This is A, PQ, B, RS. Okay, observe them. Though A, that is this line, that is PQ, appears to be smaller than B. Okay, maybe because of these arrows. B is RS, okay, length RS, but in fact both PQ and RS are of same length. Okay, this gives rise to the validity of axioms. How can we accept them under these conditions? These are confusing. Okay, so there is a question that we cannot accept them. Okay, however, we should know that the particular axiom is true without doubt. Okay, so we have to follow certain steps to ascertain the validity of axioms and check that axioms are true or not. Okay, so now we will see the steps. Okay, these are the steps to be followed to check the validity of axioms. Okay, first one here, keep the numbers of axioms as minimum as possible. Okay, for instance, based on only axioms and 5 postulates of Euclid, we could derive hundreds of theorems. Okay, these are, we have seen this. Okay, so means self-explanatory statements. Okay, or self-explanatory truths. Okay, now these are the steps to be followed to check the validity of axioms. This continued from last slide. We have seen first step on the last slide. So the second one, make sure that the axioms are consistent. Consistent means axioms are supposed to be true under all conditions. Otherwise, axiom is said to be inconsistent. Okay, supposed to be true under all conditions. Even one example is sufficient to prove the axiom is not true. Okay, now consider these two statements. They are very interesting. Okay, try to follow this. Statement 1, no whole number is equal to its successor. What does this mean? 1 is successor of 0, 2 is successor of 1, and let us read this. That means 2 is successor of 1. Okay, 1 is successor of 0, and 0 is not equal to 1, and 1 is not equal to 2. This is what is said by the statement 1. Okay, and statement 2, a whole number divided by 0 is a whole number. This is what claimed by statement 2, second statement. Okay, which means that 1 upon 0 is equal to a. Okay, and a is a whole number. Okay, let us know that we are neglecting the fact that dividing by 0 is indeterminate for time being. Okay, this is actually not to be done. Okay, this is different aspect. Okay, so we'll forget this and we will go ahead just to see the validity of axioms. Okay, so we continue from here. But if 1 upon 0 is equal to a is possible if a is equal to 1. Why? Because a has to be whole number. A cannot be fraction. Okay, a cannot be 0. It has to be 1 only. Okay, because 0, if your numerator is 1, then you cannot get 0 here. It has to be 1. It cannot be fraction. Okay, because under this condition it has to be whole number. Okay, so got it, why a has to be 1. Okay, it's possible if a has to be the whole number. Okay, which means, and if this is 1, that means cancel this and this and you get 1. Only if 1 is equal to 0, then only you can cancel them. Okay, like that we cancel a 2 upon 2, you get 1. Like that 1 upon 0, you get 1 because 1 is equal to 2. Okay, got it. 1 upon 0 is equal to a is 1 because a has to be whole number. Okay, second thing, if that has to be 1, then 1 should be equal to 0. That is what is given here, which means 0 equal to 1, which contradicts the statement 1. Okay, so these are two contradictory statements. Okay, because statement 1 says 0 is not equal to 1, and second statement we arrive here as 0 equal to 1. Hence, we can infer that any one of the above statement is true, and we see statement 1 is true. Okay, really very interesting. Think over it. Okay, And we go ahead. A false axiom will result in contradiction sooner or later. Okay, if axiom is false, then it will result in contradiction. Okay, let us see one example to find the meaning of contradiction. Consider both these statements given above. So we know 0 is not equal to 1 and 1 is not equal to 2. We are talking about those two statements seen on the last slide. Okay, now consider this example. X square minus x square is equal to x square minus x square. Okay, this is true. Both the sides are equal. So we will factorize both the sides in different way. In left hand side, x square minus x square, we are taking x common. Okay, so taking x common from this, we are getting x minus x in bracket. And right hand side, second one, x square minus x square. Okay, factorizing it and x plus x and x minus x. Okay, now these two are equal, so we are writing them like that. X into x minus x is equal to x plus x, x minus x. Now cancelling this x minus x and x minus x, we are getting x equal to x plus x, that is x equal to 2x. Cancelling x again, we are getting 1 is equal to 2. But we have seen in the statement that 1 is not equal to 2. And here we are getting 1 equal to 2, which contradicts each other. Okay, got it? Contradiction means when two statements contradict each other, appear to be true. Okay, this appears to be true. Okay, but we are ending with 1 equal to 2. Okay, I will explain you where the mistake was. Okay, we'll just see this. Such type of contradictions arose because of the false axioms that the whole number divided by 0 is a whole number. The statement 2 was wrong or false statement according to this. Okay, now come to this. Okay, we have cancelled x minus x and x minus x, that is 0 and 0, and we cannot cancel x minus x because we cannot cancel 0. Remember this. If anyone tries to fool you, then just make a comment that you cannot cancel 0. Okay, so the statements we choose as axioms need a lot of thinking and logic. Okay, we need to see that these statements do not lead to logical contradictions. Sometimes it may so happen that an axiom, when applied to the actual problems, lead to new discovery. Okay, we apply this, we have seen this. Okay, in Euclid's postulates or Euclid's geometry. Okay, so when applied to actual problem leads to new discovery, as in case of Euclid's fifth postulate. Okay, we have seen this. I'm still again quoting it again. Okay, just see this, try to understand this. Now the postulate states that postulate 5, if a straight line, if a straight line falling on two straight lines, falling on two straight lines, okay, makes the interior angles, makes the interior, these are the angles, okay, interior angles on the same side of it, that is on the same side of this line. Okay, interior angles, it's talking about interior angles taken together, that means addition of this and this. Okay, taken together less than two right angles, that means if this and this added together is less than 180. Okay, then two straight lines, then these two straight lines, if produced indefinitely, okay, produce on this side, meet on that side on which the sum of the angle is less than two right angles. Okay, and they will meet on this side because sum is less than 180. That is what it means. Okay. Now this is the fifth postulate given by Euclid. We have studied this. Okay. But this has given rise to another branch in geometry. In the process of providing this postulate, mathematicians gave rise to non-Euclidean geometry. Okay, we have seen this also. Okay, we again recall the definitions we have seen and try to differentiate them. Axiom: statement which is assumed to be true or self-evident truth and are proved is called as axiom. Conjectures: a conjecture is a statement which is believed to be true. Its truthness depends on the mathematical understanding and experience. This may be true or false, but if a conjecture could be proved to be true, then it becomes a theorem. Okay? And theorem: a mathematical statement whose truth has been established or proved is called a theorem. Okay? So by add all these definitions, and now we will try to solve some exercises. Okay. Now exercise first. Again we are coming across the Pascal's triangle. Okay, you have seen this earlier. This is line number and some of the numbers in different way. Now you will see here 1 1 11 raised to 0, 2 1 1 11 raised to 1, okay. 3 1 2 1 11 raised to 2, 4 is 1 3 3 1 11 raised to 3. See, this number is 1 less than the number of line. Okay. Fifth one is 1 4 6 4 1 is 11 raised to 4. Okay. Sixth one is 1 5 10 10 5 1 11 raised to 5. Make a conjecture about line 4 5 6. Check whether the conjecture holds good for all. Okay. Answer: we are making a conjecture now. According to the above pattern, this pattern, fourth line sum will be 11 raised to 3 or 11 cube, and should be 1331. Okay. According to this should be 1331. Now, according to the above pattern, fifth line sum will be 11 raised to 4 and is equal to 14641. Okay, according to this pattern. And that of sixth line should be 11 raised to 5 and it will be 15101051. Okay, but 11 raised to 5 according to this pattern it should be like this. Okay, but 11 raised to 5 is equal to 161051 and not equal to 15101051. Okay, so conjecture holds good for fourth and fifth line but does not hold true for sixth line, as 11 raised to 5 is equal to 161051 and not as given by the pattern 15101051. Okay, so that's the answer. Second example of pattern, we are going to study some pattern. Okay, we have seen this example but in different form, different pattern. Okay, now the different pattern. Okay, look at these triangular numbers, add two consecutive triangular numbers. Okay, t1 is 1, t2 is two lines consecutive 1 and 2, the addition is 3, t3 three lines 1 2 3, addition is 6, t4 1 2 3 4 in consecutive four numbers, addition is 10. So for example we have to add these T1 plus T2, T1 plus T2, 1 plus 3 is 4 is 2 square, this square. Okay. T2 plus T3 is 9 is 3 square. T3 plus T4 is 16 is 4 square. Okay. Now looking at this pattern, we can answer this and try to construct a conjecture. Answer T4 plus T5. If this is the pattern, then it will be 25 or 5 square, this square. In general, Tn minus 1 plus Tn will be equal to n square. Okay. We can predict this looking at this pattern. Okay. So example number 3, look at the following pattern. 1 square is equal to 1, only one digit, so 1. 11 square is equal to 1 to 1, 2 digits here. The number of digits are 2, so ascend till 2 and descend to 1. 111 square, there are 3 digits. Okay, so 1 2 3 2 1, 3 digits, so ascend till 3 and descend to 1. Okay, now 4 digits, 4 ones square. Okay, so that will be 1 2 3 4, 3 to 1, so 4 digits, so ascend till 4 and descend to 1. Square of 5 digits, 5 ones, 1 1 1 1 1, it will be equal to 1 2 3 4 5, 4 3 2 1, so 5 digits, that is we are talking about these digits, number of ones, so 5 digits, so ascend till 5 and descend to 1. So make a conjecture and find the squares of these two numbers. How many are there? 1 2 3 4 5 6, so 6 ones square, and these are 7 ones square. Okay, answer, we can conjecture about the above given pattern is, see, this is pattern, we have studied this pattern. Okay, and we have seen that the number of digits, we will read it here. Okay, count the number of digits, that is 1 here. Okay, and write from 1 till the number of digits in ascending order and then descending order till 1 here, like that. Okay, so if this is a pattern, then the answer for this will be 6 digit square. Here is given 1 1 1 1 1 1 square will be, there are 6 digits. Okay, so for the 6, 1 2 3 4 5 6, and again descend 5 4 3 2 1, 6 digits, and this is correct. Okay, similarly for 7 digits, 1 2 3 4 5 6 7, 6 5 4 3 2 1, 7 digits, and this is also correct. Okay, so this is how we take advantage of the pattern. We study the pattern and actually we go to find these big answers without even multiplying them. That is the advantage of the pattern and studying pattern, but pattern has to be correct. Okay, and this we have seen, this is correct. Okay, so we move ahead. Almost we have finished the topic, this particular topic. Okay, this is Dr. Bharat Parab helping you in your studies. If you have any difficulty in this topic of theorem, conjectures and axiom given in appendix 1, let me know through comment section and I shall solve it. Thanking you. Good luck. Okay.